go ahead and get started. And good morning, everyone, and welcome back to our weekly CMR conference series hosted at VCU. We're excited to launch it for another academic year. I hope everybody's ready to get started with the basics of CMR. We're joined by Dr. Hundley, who's the chair of cardiology at VCU and the director of our Pauley Heart Center. Has a decades-long career in CMR and its use toward various cardiomyopathies. And just a reminder to everybody that these sessions are CME and MOC accredited, so don't forget to text the code on the screen to the number provided and claim your credit. And with that, why don't we go ahead and we'll switch over to the whiteboard and let Dr. Hundley take over.
Yeah, good morning, everyone. Shannon, can you hear me okay?
Yes.
Oh, good.
Loud and clear. It looks good. I see the whiteboard.
Oh, good. So what I thought we'd do is it's kind of a little series for everybody that's on the Zoom where we think about how does this MR scanner function and operate. And if we understand just a couple principles, then I think a lot of times we can figure out how to optimize what we're doing at the time that we're examining a patient, right? So the first part I wanted to go over was basically how does this machine make its images, right? And fundamentally, what we're doing is imaging some of the effects of protons. You know, if we think about the other modalities that we have in cardiovascular medicine, you know, we have the cath lab, right? We have echocardiography. We have some of the radioisotope imaging methodologies, right? So in each of those, we are transmitting something into the patient and then looking for an effect, right? So let's take them one at a time. In the cath lab, we're pushing through x-rays, right? And then we look to see where they are blocked, right? Just think about a plain PA and lateral chest x-ray, right? The person is standing there and the x-ray kind of goes through and back behind areas where the x-rays don't penetrate. That part of the film is not exposed, right? So the x-rays don't penetrate through the bones. So that shows up white. And then where the x-rays go through the air, right, that turns dark or black, right? If we think about echo, we're pushing ultrasound into a target, and then we're looking at the reflection of some of that ultrasound coming back. Think about Doppler echocardiography, where you're trying to measure something moving through the field of view that you have, like red blood cells, right? And we can color encode that for speed and velocity. We have 2D imaging. We even have situations where we give these small little tiny bubbles, microbubbles, right? And we transmit the ultrasound in. We get those bubbles to vibrate, and then we look at the frequency at which they're vibrating, and we transfer that and make an image. And then in radioisotope imaging, if we think about a MUGA scan, you know, we don't do as many of those anymore, but you show up, you have your blood withdrawn, your blood cells are mixed with the radioisotope, they're re-injected, and then we have this camera that sits out in space and looks at the relative counts in your body. Similarly, if we do a perfusion study with the radioisotope imaging, it's the same kind of thing where a radioisotope is being given, and it might be avid for potassium, it might be avid for whatever it may be, but we're looking for that radiation emanation outside. Well, MR is different. What MR is doing very simply is looking at the impact of protons, so hydrogen nuclei that are within your body. So let's talk about that a little bit. And I'm going to use a circle here to represent hydrogen nuclei. And what happens outside of the magnet, is those protons in our body bound to either oxygen and water or carbon in fat primarily, are spinning randomly. For those of you that are can't see on the screen, I'm kind of moving my hands, but you can, these spins that are random are kind of up here outside of the magnet, okay? Now, what happens when we go up inside the magnet, okay? First of all, why is that magnet in that room? We have a CT scanner or a cath lab inside of a room. It's inside of a room because there's lead lining the walls, right? And we don't want the ionizing radiation to get out. Why is the MRI scanner in a room?
So so strong.
No. Well, one reason it's got, if you ever go into an MRI environment, there are all these signs, right? They talk to you about the magnetic field and all that kind of thing. Well, one issue, what happens if we just think about an MRI scanner, it's this round device with this hole in the middle, right? Let's put our MRI scanner over here. Back in my day, it's kind of date you. We didn't have the wrapping. It was a whole bunch of wires. But anyway, if you look around this bore, so this is the bore, and wrapped around that bore is copper wire. Just like when you were in 4th grade, you would take a nail and you would wrap copper wire around. And remember, you hooked each end of the wire to a battery, and then you created a magnet, right? So there's lots of copper, about $600,000 worth, wrapped around. And what happens is when that magnet is put in, there's an electronic charge put into that, right? And then wrapping the wire in this space is helium. Now, it's not the helium like when you were younger and going to the birthday party and everybody undoes the helium balloons. It's not in the gaseous form. It's in a liquid form. And what that does is it super cools the wire to 0 degrees Kelvin. And at 0 degrees Kelvin in that wire, there's no resistance to electricity, the electrons moving around. So it's kind of interesting. Once you put that charge in, that magnet is, you'll always see the signs always on, right? It's never turned off because that current's put in there. So inside the bore of this magnet, the magnetic field is 40,000 times that of the Earth. So what does that do to these protons? When you go up inside the magnet, back over here, it makes all of those protons align that spinning, every single one of them in your body, in a specific orientation. Now, we got to come back and answer the question, why is the magnet in the room? So we're going to get that. Why is that all wrapped in that room? Well, one reason is that 40,000 times the Earth magnetic field, if you take ferromagnetic metal and you put it into that environment, it's going to go to the center of the bore of the magnet with force that cannot be stopped. Right? So the accidents that happen with an MRI scanner is someone goes in there when there happens to be a patient in there, or sometimes not, and they take ferromagnetic metal and it's going to go to the center of the bore. It can be big things like someone's delivering a desk and they've got the wrong room number. It can be small things like a hammer, whatever it's going to be, an oxygen tank, it's going to go straight into the bore of that, and you're not going to be able to stop it. So one of the reasons we've got all these zone 1, zone 2, zone 3, zone 4, all that stuff is you don't want to take ferromagnetic metal. So if you're a cardiology fellow or you're a radiology resident or you're a nurse, stethoscope comes off. Okay? Right? All of the things. Something else to keep in mind, you don't want to take your credit cards in there because it's going to erase them. You don't want to take a computer in there. It's going to erase the hard drive. Right? People get their computers stolen. And one thing that bad guys do is they take these laptops up next to these MRI scanners, they just wipe out the hard drive. You get to start all over again. Okay? So we want to keep that in mind. That's one reason that it's in the room, but not the primary reason. So we've still got to make a picture, right? We're just sitting in there. So what happens next? So the next thing that happens is there is delivery, believe it or not, of electromagnetic radiation, but it's not ionizing. It's in the form of an FM radio wave. And so what does that do to those hydrogen nuclei? They tip their spins like this. Okay. And then after the FM radio wave has passed through, what happens is the protons go back to their orientation in the magnetic field like that. And when they do that, they release energy. And that energy is picked up by an antenna. Now that antenna can be located in a couple of different regions. One place that the antenna can be is actually in the wall of the scanner. Right? But another place the antenna can be located, and where we use it for most of the imaging, is you wear this kind of light foam thing that sits on you, and that's got lots of little antennas inside it. We'll talk about lots of little antennas in talk number 3. So antennas then pick up the energy, and that's what's used through a process called a Fourier transform to make the picture. Okay. So the second reason the magnet is in the room is because we've got to stop any other electromagnetic radiation from interfering with the picture taking. Now, it's very interesting because the frequency that it uses is 88 point something megahertz, which, since you live in Richmond, Virginia, you're going to see something called, I think it's called WTVR. It's channel 6. Its tower is located right down Broad Street. Do you know that it is the first television south of Washington, D.C. in the United States? And it transmits at exactly the same frequency that your MRI scanners use. So another reason, but where else can you get that? All these lights these electrical outlets. So the second reason that that thing is in a room is to keep the electromagnetic radiation from the environment from interfering with the scanning process. Okay? Two reasons. So in the cath lab, we want to keep something that's in the room from getting out. In the MRI environment, we want to keep things from outside getting in. Ferromagnetic metal, ionizing, not ionizing, but electromagnetic radiation that's not ionizing, okay? So it's kind of nice if you're coming back and you've got a research study or you've got patients and you're following them longitudinally over time. This process does not use ionizing radiation for X-rays. Now, you hear about this thing called, it gets scary, right? There's T1 and there's something called T2, right? We hear about T1 and T2 and blah, 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 and all these things. So what do those refer to? Well, the first thing, let's talk about the T2. The T2, very simply, is the time that it takes for these protons right here to go from this orientation to this orientation. And how often, what is roughly the time it takes to do that? On average, about 30 milliseconds. It's very quick, right? So you're inside the scanner, FM radio wave goes through, T2, you can measure that. The other thing that happens when this FM radio wave comes in, back when I was a kid, there were these things called whizzers. We didn't have a lot of electronics back then. So they had these little toys, but it was basically a top. And you held it in your hand, it's inverted, and you go, and then you sit here and it would just spin on the table. So what happens is, the other thing that happens with this FM radio wave is these protons wind. And then when they go over to this space in their original, they unwind. Okay, so they wind this way, and then they unwind this way. And that winding and unwinding time is T1, right? It's really easy. That's not hard to think about at all, right? And the unwinding time, if we have these different field strengths, remember we wrap this thing with copper wire, right? And we have basically 1.5 Tesla, and we have 3.0 Tesla, okay? So that's the strength of the magnetic field, all right? For 1.5 Tesla, what does that strength do? That's the intensity of the winding. So at 1.5 Tesla, you kind of wind medium. At 3 Tesla, you wind even tighter. So at 1.5 Tesla, there is this much energy released. At 3 Tesla, there's a lot more energy released. So the winding and unwinding time for the T1 is a little different. At 1.5 Tesla, that winding time is about unwinding time is about 950 milliseconds. At 3 Tesla, what do we say is the normal T1? Yeah, about 1150 to 1200 milliseconds. Okay. So what's interesting, we get a little bit more takes a little bit longer at 3T, but we get more energy that's released. And that's why at 3T, you have a little bit better image characteristics. And we're going to talk about that in the next series of drawings, okay? So let's review. We're imaging protons. We're different from other imaging modalities. We're not transmitting X-rays in. We're not transmitting ultrasound in. We're not giving radioisotopes. We're simply looking at the behavior of protons. We're going to talk about tissue characterization in another couple talks, right? But the protons primarily are bound to oxygen and water and carbon and fat. We can actually see the difference, okay? We're imaging protons outside of the magnet. They're precessing or spinning in a random fashion. You go inside the bore of the scanner and they all line up in a specific orientation. Then we pass an FM radio wave through. What happens is all of those protons tip their spins. Remember also, they wind up, right? Then, after the FM radio wave has gone through, they go back to their original orientation. One of those processes happens very quickly. That's T2. And T2 times, they're so fast that they're the same at 1.5 and at 3 Tesla. But the winding and unwinding process is different. And that's the T1 time. And at 3T, there's a tighter winding. And what that means, it's like a spring, and then it unwinds with a lot more energy, and you get a lot more signal. So you can see more of the effects on those protons than you do at 1.5. Okay? Everybody got it? Any questions on that part? Also, magnet is in the room because we don't want things to get in there. Non-ionizing electromagnetic radiation. Channel 6 is right down the street. How coincident is that for you, fellows? You move to a place that you're perfectly suited to have your MRI scanner messed up, imaging. Okay, so you got to keep the door shut. That's the big thing, right? And you don't want to take ferromagnetic metal in there. Now you can take non-ferromagnetic metal. That's the trick. And what are 2 non-ferromagnetic metals that are very common in your environment that you can take in the room? Aluminum and steel. Stainless steel. Stainless steel, I mean, you see them, you know, Dr. Canada has a bicycle in there all the time. That thing's got tons of metal in it. It's all aluminum and stainless steel. So there are certain metals that can go in there. There's certain oxygen tanks that can go in there, but most of them cannot, okay? And so that's why you're going to see stickers. MRI safe, not safe, blah, 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 blah. So you will see metal go in there, and you're going to be confused. Well, non-ferromagnetic metal can go in there, okay? All right, now I need a new page. How do I do that? Okay, now we're going to talk about a little bit about making the image. Can you show an image, Corey?
Yeah.
Yeah, this guy. Okay, so everybody can see the screen. This is a color image. It's an in-color image, so that's the one we're looking at. You can see all these moving things on the left. We're going to talk about how we make the movies next week. We're going to talk about these still images. And what I want you to notice, the image is made of, we call it in 2 dimensions, pixels. See if you can see you can't see my pen. If you look at the top left part of the color image, the top left part of the color image, you're going to see fuzziness, but there are lots of little squares. Those are called pixels. Pixels you have those on all your screens. Pixels are defined in 2 dimensions. Just like a square, you have, one axis, we call them length and width, something like that, right? You think about when you were doing geometry and stuff like that. Think about a square. You've got the length of one side of the square, and you've got the width, or you have a rectangle. So most of these are going to be squares. Those are called pixels. Now, when you look at this picture, let's come back to the whole thing. It has some thickness to it. It has some thickness. So it has a 3rd dimension. So each of those little squares that you see, if we just talked about them in 2 dimensions, they would be a pixel. But when we add the 3rd dimension, the depth, because of the thickness, then it's called a voxel. It's called a voxel. Now, this is what's called a T1 map. So you can see all the little squares up in the left, that's out in air. They're kind of random. But around here, and Corey, you can use your arrow to point. This is a short axis view of the left ventricle, and the dark orange is the muscle in the wall. The yellow in the center is the blood pool. And then over here on the left side of the image, the right side of the patient, is the right ventricle, and it has a much thinner wall. And so then on the far left side of the picture, there's a little scale. And at the bottom is 0 milliseconds. And at the top is 2000 milliseconds. So what has happened on this particular picture is it's a map, a color map of T1 values for all of the voxels that are comprising the image. Okay, so all of those voxels have got lots of protons in them, right? And so after they go inside the magnet, spins line up, FM radio wave has gone through, and then after the FM radio wave passes, all those protons go back to their orientation. They release the energy, but they take time to unwind, and we've measured that. And we said normally, and this is at 3 Tesla, this particular picture, normally that happens in 1150 to 1200 milliseconds. So what you can see here, Corey, you can point to this. There's some little regions of interest drawn around the voxels. And over here it says mean, and there's 1271. So the average time of the hydrogen nuclei within the voxels right there to go back to that orientation was 1271 milliseconds. Now, why is this picture in color? If we look over on the left side of the screen, there's a whole bunch of black and white images, and there's only 2 of them in color. So one of the reasons that this is in color, or the reason that it's in color, is look at the scale. Remember the T1, we have 0, and it goes all the way up to 2000. So that's 2000 increments that can happen. If we want to display, if you think about black and white, so the images on the far left are in grayscale, black and white images. Our eyes can only see from the brightest white imaginable to the darkest of black. If you're in a cave, there's no light whatsoever. You can only see 80 different shades from the brightest white to the darkest of black. But you've got 2000. So what do? We have to switch to color because your eyes can see many shades of color. So that's why these map things are in color. Okay? They're displaying for you the hydrogen nuclei in the voxels that make up the picture. And very nicely, you can see what they are with the LV myocardium, look at these ones in the center with the blood pool. What's in blood? Water. Lots of hydrogen nuclei bound to oxygen. Look over here at our scale. Go up here and, they're going to be very high numbers. Right. Makes sense. That's the T1. Okay. Now, quickly, this talk is not about what does T1 tell you, but what I want you to think about with T1, it's kind of a non-specific thing. What do I mean by that? In medicine, we have a lot of values when they start to become elevated. We know something's going on, but we don't know what. Think about SED rates, right? Have somebody, we come in, maybe they have some inflammation, we get a SED rate, it's elevated. I don't know what's going on, but there's some inflammation, something's going on. T1 tells us if the T1 for the myocardium is normal, that's great. We have a normal relationship between healthy myocytes and the other stuff that's in the wall. We're going to talk about that lecture 4. I'm going to do the cardiomyopathy thing. But within a chunk of myocardium, there's some myocytes in there, there's some fibroblasts in there, there's some small blood vessels in there, there's a bunch of stuff. If the T1 is in the range of normality, then we have the right ratio of normal healthy myocytes and all the other stuff. When the T1 becomes elevated, something's going on that's wrong. Maybe there's not as many myocytes. Maybe there's extra water in there. Maybe there's more of the fibrous tissue in there. Maybe there's another whole substance in there that shouldn't be, like cardiac amyloid. If the T1 is really low, what was normal at 1.5 T? 900 milliseconds. What's normal at 3 T? 1150, 1200. Suppose at 3 T, it's 700. That tells you that there's some extra fat in there. Okay? So T1 up and down, it's kind of a non-specific thing. We just know something's wrong. We're going to have to use other parts of the image. And we're going to talk about that in a different lecture. But this is a nice example of how we use the T1s. Okay, can we go back to the whiteboard? Now, we've got to figure out how in the world did we make that picture? We talked a lot about the protons and the spins and the antennas and all that kind of stuff. And we did introduce the concept of voxel. All right, so remember a pixel has got this dimension here. I'll call this the width, I guess. And we have the length. So what is a voxel? That's right. The voxel has the depth, right? And inside this voxel are the protons. These are all the little guys in there, right? That are doing their spin thingy. Right? That's what we're trying to capture. If there's lots of those guys in there, if the voxels are big, there's lots of protons in there. And so when we do the whole little, this gizmo, remember? And they orient, oops. Go down here, we get this. We go back, we do this, remember? If there's lots of these guys in there, all of these are these little points, then we can get a lot of signal in the image. But the voxels are really big. And you don't get a lot of clarity for defining the target. Your spatial resolution We'll talk about that in a minute. See, here's our picture. Remember we had that square? And we had in the middle of it, we had the LV. Remember, we just looked at this. We had the LV, we had the RV. Right? And so we gotta, if we have big voxels like this, right? What's going to happen is we're not going to be able to make out the boundaries of the wall. Our spatial resolution is low. If we increase the spatial resolution, what does that do? That means we have little tiny voxels. And look how many protons are in there. Not very many. So when we do the whole little, doodah there with the FM radio wave and all that kind of stuff, the problem is we don't have very much signal. But for this, it's great. Look at this. Holy smokes. I mean, I can make out boundaries and all this kind of stuff really, really well. All right. So this is a high spatial resolution. But it has low signal to noise. This is a low spatial resolution, but it has high signal to noise. Next week, we're going to talk about temporal resolution. There's three things that are always at play when you try to create the picture. Today, we're talking about just a still frame. So it's the spatial resolution. High spatial resolution, small voxels, low signal to noise. Big voxels, low spatial resolution, high signal to noise. So how do we set, we're trying to do this cardiac stuff. And how do we decide, how do we set the spatial resolution of the image? There are two parameters. I mean, when you sit at the scanner, and you should sit with Shelley or Chris or Terry or whoever, then you should sit one day. Because what's kind of neat about MRI, see, when you've got an echo machine and we're called in the middle of the night and you're up in the CCU and we want to know, is there a pericardial effusion or whatever, I mean, you just turn the thing on, right? It's going to transmit and receive. It's just doing its deal. For this technology, every time you sit down and do one single thing, you're writing a computer program. Now, many people for many years have written these for you. And one nice thing is, for people that work with different vendors, is we all share. We share with UVA, we share with Duke, we do all these kinds of things. There's a constant communication of all of us. It's kind of a nice collective. You'd be surprised. We even compete with one another with grants, clinical, and how many patients, and blah, blah, blah. We ubiquitously share all the things that we do. That's kind of crazy. But how do we set the spatial resolution? Does anybody know? There are two things that we can adjust. So the first thing is the dimension of this entire picture. Okay, that dimension and this dimension. And does anybody know what that dimension is called? Yes, the field of view. So in the world of MRI, you're going to hear this term, the field of view. And if you're sitting there at the scanner, it's going to be called FOV. Right? So the first thing you're going to do is you're going to set the field of view. So the field of view, if you go in and start, a lot of people will say they'll start at 36 or 40 centimeters. It's all in centimeters, millimeters. Okay? So you want to have some idea of, well, what shape inside the bore of the scanner. Remember, let's don't forget, we got our scanner sitting over here. And inside of the bore of the scanner, what size block do we want to create? And the dimensions of the block on this side and on this side, this is the field of view. Okay? You want the field of view as closely to match the size or the shape that you're imaging. So a bigger person might have a larger field of view. The problem with this technology, so here's our person sitting in here. Now remember, they're laying in there, feet are coming out towards you. If we set this field of view too big, make it way up here, we're throwing away all this airspace that we don't really need to be imaging. If we set the field of view too small, there are two bad things that happen. One, we're missing the area that we're trying to image. And the second thing is the scanner kind of has an intrinsic field of view, and it folds that part of the image that's outside of the field of view. It folds it into your picture. It looks insane. You know, instead of here's the patient laying in there, what you'll get is something that looks like this. And then this top part here is folded down into your picture like this. All right. So the first thing is the field of view. So we're going to get that right. Now, what's the second thing? How many lines do we want to stick in here? It's just like your television set or any screen that you're working with. How many lines do we want to put in the field of view? Right? This is going to be our dividers, right? How many lines are going to come across here like this? And how many lines coming down this way to make these pixels in 2-dimension or voxels in 3-dimension? Now what that's called, what is that called? Your matrix, okay? Your matrix. So the number of lines, it's how many lines are you going to fit within the field of view? And this is your matrix size. Right? And typically, you'll run in a matrix size of 64 by 64, whoops, 128 by 128, 256 by 256, 512 by 512. So every time you sit at the scanner, you are setting the field of view and the matrix size. And that's important for this purpose over here, the high spatial resolution and the low spatial resolution. So high spatial resolution, we might have a field of view, typically in a person, normal size of say 30 centimeters. That's this total distance. And then we might stick in there, I don't know, 256 lines, 256 lines to make the pixels so that we get the resolution that we need for the target that we're interested to image. Okay. One of the common things that you run into is you don't set the matrix or the field of view, the spatial resolution correctly, and you don't see what you're interested in because you may not, it's a balance. You've got to have enough protons in the voxels to see them, right? And so you're constantly making that adjustment. You can have lots of signal, big voxels, low spatial resolution. My gosh, the thing is going to blow you out of the room. You can use it as a light on a steamship in the middle of the night. The whole thing, the screen will be so bright it'll light up the room. Okay? But you're not going to be able to see what's in there because there are tons of protons, but you haven't got the spatial resolution you need, the definition to make out different structures. Okay? And so that's very important. All right? It takes more time. We're going to talk about temporal resolution next week. If you put lots of lines in here, you've got to collect the information, believe it or not, for each line. And that can make the scan longer. Now, what if we need a whole bunch of scans to make a movie, like a cine? We're going to talk about that next week. So there's always going to be trade-offs when you are, let's just take one more step back. When you show up in the cath lab, you're pretty much always going to give X radiation. You guys aren't constantly talking about how much radiation you're going to deliver and stuff like that. You do a little bit if you've got somebody that weighs 400 pounds and all this kind of thing. But the radiation exposure is about, if you're doing a nuclear study and you're handling the radioisotopes, remember you got the little syringe with the little lead thing and all that, you're given the same amount. When you turn on the echo machine, you're just turning it on. You're not really adjusting power and transmission and all that kind of stuff. It's done for you. In this technology, every single time you get every single picture, you are making an adjustment because you're writing a computer program. Now, for most of you, that's already been done. In fact, when this magnet was put in, we spent probably 3 or 4 months, none of you were here, setting up what the fields of view and the spatial resolutions would be. So you didn't have to do that every time you show up. You've got a good rough estimate, but you're going to have to make adjustments, okay? Because you're imaging protons. If you make these things so small, you're not going to be able to have enough signal emanated from those things that you can put the picture together. If you make them really big, you get all this beautiful signal, but you don't have enough resolution to define structures. Okay, so in review today, we talked about how we're making these images. We're imaging protons. Most of them are bound to oxygen and water or carbon and fat. We're going to talk about, in lecture 4, tissue characterization. One of the most fundamental pieces of tissue characterization is discriminating fat from water. In cardiology, you can have a tumor in the heart. Is that a lipoma? You have, you see a mass on echo in the wall of the atrium, and it's lipomatous hypertrophy of the interatrial septum. That's one picture. Boom, fat or water right there in the interatrial septum. Okay, so it's a simple form. How do we make the images? Outside of the magnet, there are lots of protons in our body. They're spinning in a random fashion. We go up inside the bore of the magnet, they line up in a specific orientation. Then we pass an FM radio wave through the target. The protons tip their spins. After the FM radio wave has gone through, the protons go back to their original orientation. They do so in 2 ways. One very quickly in a transverse plane, which happens almost instantaneously in an average of 30 milliseconds. That's T2. Then there's this winding and unwinding thing, and that's T1. It takes a little longer, 1,000 milliseconds, 1,100 milliseconds, da-da-da. The higher the field strength, the more you wind, and the more energy that's going to be released by those protons. And so you can use that when you have disease processes where you're trying to figure out what's in the myocardium and you want that T1 signal, you go to 3T. If you have things that you're not interested in that, blood flow, angiography, stuff like that, blood flow in vessels, the congenital heart disease patients, that's much better at 1.5T because you don't need all that stuff. When you're doing an 18-year-old with transposition or whatever, you're not trying to figure out, is there prior MI or is there something going on in the LV? You don't need that. You want to get them in and out and go quicker. 1.5 is much better for that. Okay, so there's different field strengths, and that really is affecting some of that T1 stuff. How do we create the pictures? We've got to do the spatial resolution correctly. There's two descriptors of how we create the voxel sizes, the pixel sizes. Those are the field of view and the matrix. Okay. One more piece of that I didn't mention for voxels is the slice thickness. Okay. So remember, these things do have depth, and so we do adjust the slice thickness. Okay. Any questions? Okay. So next week, Dr. Jordan, who's one of our biomedical engineers, part of the Pauley Heart Center, she's going to show you some images and go through some T1s and T2s and all that kind of stuff to reinforce that. And then I'll come back in 2 weeks. Now we've got to make cine movies. We function. Blah, blah, blah. So we have to learn how to do that. And we've got to introduce how are we going to create those movies. And then you guys have to deal with arrhythmias. So we're going to throw in another factor. And then the third lecture is going to be about blood flow and perfusion. If you have these 3 lectures and these 3 follow-ups, you're going to have everything you need to know to sit down and make things happen and be able to understand. And the whole rest of the year is just working through different disease processes. Okay. All right. That's it. Well, thanks everybody. Thanks for everyone online.
Thank you so
and
much.
It's all going to be this whiteboard stuff.
And Shannon, if you don't mind throwing up the see me slide again. Thank you, Dr. Hundley. That was really wonderful. And we had originally planned to maybe take next week off, but since you've covered the T1, T2, we'll work through the schedule and make sure that we have these well reinforced. That's really helpful.
Yeah.
All right. Thanks, everyone.